To understand the rate of change problem we will see later in the derivative section, first we need to look at the continuity problem, guys. Continuity is also related with the limit problem. So let's look at the behavior of this function, right, you see in this graph, and then try to understand what we mean by the continuity in mathematical sense. So if you look at this graph, right, especially with the points, going through the points, look at the 1.5. When x equal 1.5, the graph, right, you see here, right, it is going to be equal 4. So my function is defined here, and then there is no problem at this point. So also look at that from the right hand side and the left hand side, I can approach to this point and I can find the limit easily. But opposed to 1.5, if you look at, right, the x equal 3 point, although it is defined here, right, I don't have any problem with the definition, but if you look at the limit problem, right, approaching from the right hand side or the left hand side, so the left hand side or the right hand side limit are going to be different, right? Also, you see that, right, that there is a jump here, right? So this jump is going to be important for us. And also, if you look at, right, that when x equal 4, although I have, right, the definition of that point for f is equal 4, right, f is equal 4, but if you look at, right, if you look at here, right, that there is a gap, and then the limit from right hand side and the left hand side, they are equal, but the definition is not going to be same. And then there is another case when x equal 5, right, there is no definition, and then the value of, right, your function from the right hand side or the left hand side of 5 escapes to the infinity. So all of these examples, all of these points actually shows us something, right? So the last 3 points is not something like the x equals 1.5, since here, as you see, there is a continuity, right, in the normal usage of the continuity. And here, if you look at, right, the 3, 4, 5, okay, there are not continuity as in the sense of the 1.5. I can give you the, right, a heuristic approach saying this. If you can draw, right, the graph without lifting your hand, that point is going to be continuous. But look at here, right, when you look at, right, the x equal 3, as you see here, there's a jump here, right, that there's a jump. That's why, okay, this type of, right, discontinuity will be called the jump discontinuity, guys. But if you look at, right, the other type of discontinuity, when x equal 4, right, here, this is not the jump, since look at the from the right hand side and the left hand side, I am getting the same limit. Only I have the gap here, right? This gap can be filled, right? If you define this point, if you bring this down here, maybe you can do that or not. But if you can do that, right, this gap can be removed. That's why, okay, this is gonna be the removable type of discontinuity. And then also there are some other type of discontinuity here when x equals 5. This type of, right, as you see, right, from the graph, this type of discontinuity is going to be the infinite type of discontinuity. So basically, right, these are the 3 type of discontinuity, but there are some similar problems, right, about behavior of this function. But if you look at, of course, we need to give a mathematical definition for, right, the definition of the discontinuity. That is why, okay, the definition, right, should include all these points, all these, right, the behaviors you saw in the graph. First of all, yes, we have a function, right, we have a function, and first of all, as you see, to be able to write the continuous, as in, right, this case, right, x equal 1.5, first of all, your point, right, it should be defined. Secondly, definition being defined is not gonna be only one condition, since if you look at x equal 4, although I have the, right, the defined version of, right, that point, still it is not continuous. Why? Since this point should be here. What does that mean? This means actually first, right, I should have, right, a limit, right, as you see, right, when x equals 3, since I don't have the limit, that's why, right, the point here, it was broken, right, it was broken and it jumped. That's why, because you don't have, right, you don't have here the limit. This is why you should have the limit at that point. The third case, right, although you have the limit, as in the case x equal 4, right, you have a limit, but the limit is not equal to the, right, the function definition. That's why, okay, to be able to continuous, the last condition, they should be equal to each other. Okay, if you satisfy all these three conditions, I'm gonna be able to say, guys, f function f is continuous, okay, continuous at x equal x0. Okay, so you need to be able to check all these 3 points. If one of them, okay, fails, you can just say, okay, it is discontinuous. Of course, depending on what condition fails, right, you can just determine what type of discontinuity you have. So let's look at, okay, some examples now. If you look at this function, look at that, right? My question is about the continuity, and then I need to be able to check all the points, right, for the continuity problem. But if I determine, right, if my function has some points, right, at which it makes, right, my function, right, undefined, I can just say that those are the points, right, which my function is discontinuous. As in this case, look at that. I'm asking basically, right, the first condition, if my function is defined. So if you look at, right, the bottom part, correct, the value which makes the bottom denominator part makes the 0, that would be, right, the undefined point. If you use, right, x equal 2, this is going to be, right, undefined. This makes my function undefined. That's why, right, here, what I need to do, right, to make this function continuous, I need to throw this one right to the garbage so that I can make function continuous. So basically, this is also the domain of this function, right? So domain will be equal, right? This point, look at it, as you see, I didn't put the 2 here. If I take the 2 out, right, that's gonna be, right, the continuity region of my function as well. Another function would be, right, a polynomial. For the polynomial, actually, they are nice function, they are smooth function. Actually, we can just say that, okay, everything is nice, so they are always continuous, but I would like to show it to you. F is defined, yes, we know, right, that the domain of the, okay, function is R. There is no point, as you see, you can make the, right, this one undefined. The second one, what is the limit, right, for any point, any x0, as you know, right, you can find out the limit of this type of, right, the polynomial, x0 squared plus 5. And then in the third part, right, is this equal to, right, your function definition? Yes, since if you use, right, this point, any point in your function, which is equal x0 squared plus 5, as you see, my limit, right, is equal to my function definition. That is why, right, I passed all these 3 tests. I can definitely say, right, that my function is going to be continuous. And we can just expand this definition to the all, right, the polynomial. So from now on, this is going to be maybe the continuous theorem, right, one of the continuity theorem, guys. So all polynomials are continuous function, okay? So all continuous function. And then if you have look at the rational type of functions, this is, right, the continuous, okay, except qx, right, is not equal 0, okay? So you can just say in these ways. Another example, right, maybe last example, let me show it to you. 2x plus 7, right? So you need to tell me where this function is going to be continuous by just, okay, looking at the definition, right, of the points, right? I can just tell you where this function is going to be continuous. If you look at, right, this expression inside the radicals, right, that should be always bigger than 0. Otherwise, right, I cannot define this function. To do that, if I move the 7 to the other side, divide by 2, it is going to be equal, right, x should be bigger than or equal negative 7 over 2. As you see, if I use, right, the x value, which is bigger than that value, I can make the radical inside the radical bigger than 0. And then this will give me, right, the domain of this function. So domain of this function will be equal this one, correct? So this is the domain, and then in the domain of the functions, okay, they are going to be continuous. So there is no other value, right, which makes it undefined. Everything is going to be nice. So I can just say this function is going to be continuous, right, at those values.